Hi guys, welcome back to another lesson. Today you need to grab your calculators because we are going to jump into some pH calculations. We're going to also look at the pH scale, and then we're going to practice a lot of examples where we have to go work with the hydronium ion and also hydroxide ion concentrations. Okay, so let's start off with the basics. When we start off with pH calculations, we need to consider the first very important reaction, and that is the ionization of water. So when water ionizes, it basically ionizes into hydronium ions and also hydroxide ions. Okay, so just to illustrate this, if you have a water molecule, so you've got one oxygen, let me just use a different color, and attached to my one oxygen, I've got two hydrogens. So when my water molecules start to ionize, now remember that there's more than one. There's a lot of these molecules inside of your beaker. So millions of these molecules inside of your beaker. So you've got water molecules floating around, and what happens is it starts to break up, and what happens essentially is these hydrogens is taken up by another water molecule, okay, and then it forms the hydronium ion. So essentially you have an oxygen atom here that now has 3 hydrogen ions attached to it. Okay, this is just for illustration purposes. So now that's a hydronium ion, and you are only left with an oxygen and only one hydrogen, and that's a negative charge. So basically these molecules inside of the container break up into the separate molecules or separate ions. Okay, now you know this has a positive charge, therefore it's a cation. And this has a negative charge, and it's also known as an anion. Okay, so they keep on drifting here in your solution. So now we have a dissociation, or in this case an ionization constant, which we define as Kw. And Kw, now if you guys remember the expressions that we did in the previous video, we said that if you want to get a K expression, you take the concentration of the products, if it's in aqua or in a gaseous state, over the concentration of the reactants. But you can see in this case the reactant is liquid, so we're not going to include it into our equation. So the ionization constant of water is going to be equal to the concentration of hydroxide ions times the concentration of your hydronium ions. Okay, and there is a value for this. It's a constant value, and that value is 1 times 10 to the power of negative 14 at room temperature. So that is the constant of the ionization of water. So when you look at neutral water, or let's say you have a beaker, and inside of your beaker the amount of hydroxide ions are equal to the amount of hydronium ions. So in other words, the concentration of hydroxides is equal to the concentration of hydronium ions. If that's the case, then we can basically make a mathematical equation from this and say that, well, if these two concentrations are equal, right, so let's say one of the concentrations are x. So if this is x and this is x and they're equal, then that gives us x squared, right? Because it's x times x. X times x gives you x squared. So x squared is then equal to 1 times 10 to the negative 14. So how can I get the concentration of only one of them? You need to take the square root, and the square root of that Kw constant is 1 times 10 to the negative 7 moles per cubed decimeter. Okay, so that will be the concentration of hydroxides and hydronium ions in a neutral beaker of water. Okay, neutral or even pure water. Okay, so tap water won't necessarily have a neutral pH. Sometimes tap water has a higher alkalinity because they add different chemicals to the water to purify it. So if you're working with pure water, then this will be the concentration of your hydroxide ions and your hydronium ions. Alright, so let's move over to talking about the pH scale. Now, a pH scale gives you a measure of how acid or how alkaline a substance is. So, a nice way of remembering this is to say that pH is the power, or you can even say the potential, of your hydrogen ions or hydronium ions. So it's the power of hydrogen. So it means that the more hydrogen ions you have in your beaker, the higher the power or the potential of the hydronium ions are. So you will have a lot of hydronium ions inside of your beaker. And if you have a lot of hydronium ions inside of the beaker, the pH is going to be low. Okay, so the pH is going to be low if you have an acid. Why? Because pH is the negative logarithm of the hydronium ion concentration. Okay, and that's also how you calculate the pH. So you would say the pH is equal to the negative logarithm of your hydronium ion concentration. So if you have a lot of hydrogen ions in your solution, then the pH will be very low. And you can even check this for yourself. Okay, so you can maybe choose a value and say, okay, let's say 1 times. Now you can scroll back and see if you have neutral or pure water, it's 1 times 10 to the power of -7. So if we're working with a much higher hydronium ion concentration, let's say 1 times 10 to the power of -2. Okay, that's much higher. You can now take your calculator and actually look at what that will give you. Okay, and that's going to give you a pH of 2. You can do exactly the same with this concentration and you will get a pH of 7. You can even try it with an alkaline substance. You can take a hydroxide or a hydronium ion concentration that will be much lower. So let me quickly write that out for you. So remember that the pH is about the hydronium ion concentration, not the hydroxide ion concentration. So let's say your solution is very basic. That means that you will have a very low hydronium ion concentration. So we can choose a value that's very small. So let's take 1 times 10 to the -12, for example. You can see that value is very low. So if I quickly work that out on my calculator, that will give me a pH of 12. Okay, so that's how you can go about working out the pH on your pH scale. So the difference between two numbers on your pH scale, difference of a magnitude of 10. So for example, a pH of 5 means that the hydrogen ions is 10 times more than that of a pH of, 10 times less, because now remember here we have more hydrogen ions because your pH is lower. And as you move all the way from there to your alkaline substances on your pH scale, the hydronium ion concentration decreases. Okay, so just remember that. So a pH of 4 will have 10 times more hydronium ions than a pH of 5. Okay, and then here we talked about neutral, a neutral or pure water that has a pH of 1 times 10 to the negative 7. So a few examples just to go through: battery acid, which is also sulfuric acid. This one is a little bit debatable. Hydrochloric acid, depending on how concentrated it is, I think would be actually more acidic than vinegar, because vinegar is quite diluted. In tomato juice, black coffee, urine or saliva, pure water, seawater, baking soda, and antacid, which is basically magnesium carbonate tablets, ammonia, soapy water, bleach, and drain cleaner. Okay, just as I've illustrated on my video of kitchen chemistry, where I also tested household chemicals. Okay, so just a quick summary on the formulas that we will be using during this lesson. So the first one, pH, is equal to the negative logarithm of the hydronium ion concentration. Okay, it doesn't make a difference if you said hydrogen ion concentration. It's the same thing, right? Then the hydronium ion, if you want to calculate the hydronium ion concentration and you have the pH, then the hydronium ion concentration will be 10 to the negative pH. Okay, so that's how you would go about calculating the hydronium ion concentration. And then the last one that you just need to know is the Kw expression. You can actually work out the concentration of the hydroxide ions or hydronium ions given this constant, which is 1 times 10 to the negative 14. Okay, the ionization constant of water.